Okay, so question 6. What is the ionization energy of a hydrogen atom that is in the n equals 6 excited state? Okay, so I'll do this question in 2 parts, and we'll note that the energy of an electron at level n in a hydrogen atom is given by the following equation. Okay, so I'll show that E at level n is equal to negative RE divided by n squared. And then I'll just show that RE is equal to 13.6 eV. This is also called Rydberg energy. Okay, so step 2. The ionization energy is the energy required to raise the electron to the level n equal to infinity. So to a very high level. So I'll kind of show what this would look like if we wanted to solve for ionization energy. This is equal to the energy of the electron at level infinity minus the energy of an electron at level n. So let's sub in our equations from the first step. We had 13.6 divided by infinity to the power of 2 subtracted by negative 13.6 over, in this question, it is 6 squared. And notice when you have a number being divided by an infinity, since it's a very large number and you're dividing by it, then the value just goes to 0. So I'll just change this to level 6. So since that whole part of the equation goes to 0, this kind of simplifies our work because now we're just left with positive 13.6 eV divided by 6 squared. So 6 times 6, 36. So let's calculate this. 0.3777. So I'm just going to say 0.38 EV. And typically the ionization energy is given in joules, so I'm just going to convert EV to joules. So the conversion factor is 1.602 times 10 to the power of negative 19 joules in 1 EV. So this cancels out our EV, and we're left with our answer in joules, which is 6.052 times 10 to the negative 20 joules. Okay, so let's see what the junior tutor said. Okay, so the junior tutor talks about the Rydberg expression. So this is another another method of finding ionization energy. And they also show the whole Rydberg expression. Lambda is the wavelength of the emission line, N1 is the lower energy level, N2 is the higher energy level, and R is the Rydberg constant, 1.097 times 10 to the 7 inverse meters. As N2 continues to get higher, the term N2 approaches 0, implying that N2 approaches infinity and the electron effectively leaves the atom, thus forming a hydrogen ion. The Rydberg expression determines the emission when an electron falls from a higher energy level to a lower one, emitting a photon. We will use it to find the energy required to move an electron from the 6th energy level to infinity. So they showed how N1 is when you would plug in 6 to the power of 2, and since 1 over anything to the infinity is going to equal 0. So this kind of simplified their expression, and they found the wavelength that corresponds to this. But this is in inverse meters. So then to convert to oh no, this is just in meters. So they already solved for lambda. And then to determine the amount of energy, we use the Planck equation. So the Planck equation is E is equal to hc over lambda. So h is Planck's constant, which is 6.626 times 10 to the negative 34. C is another constant, which is the speed of light, 3 times 10 to the 8. And then lambda is what they found in the previous step. And they got the same answer, around 605 times 10 to the negative 20 joules. So this is the energy required to ionize a single atom. To get the energy required to ionize a mole of atoms, we multiply by Avogadro's constant. Multiply mine by where's to the power of on this thing? Using this is 1.602 times 10 to the negative 19. Then I'm just going to multiply by 0.38. 6.0. That's around the same value. So you can do either method. I think that the equation that I used is kind of simplified by doing, like, if you were to combine the two steps from the junior tutor's answers, then you end up pretty much getting the same thing. I'll just also write in that you can also calculate energy of an electron at level n in a hydrogen atom by using where RE is equal to 13.6 eV, which is Rydberg energy.